Okay, this is going to be the second analysis video in the series of elastic collision analysis videos where I'm going to be using this formula to predict the velocities, so theoretically predict the velocities after a collision and see whether or not they match the actual experimental results. And also this time I'm going to check whether or not momentum is conserved and kinetic energy. I didn't do that in the previous one, so I'm going to do that right now. I'm going to do that in this video. And also, this is an attempt to prove whether or not momentum is a vector, whether or not momentum, whether or not direction matters. So whether or not it can be negative. So the video that I'm going to, the experiment that I'm going to be doing, that I'm going to be using is from the same YouTube channel, the same person performing another, well, the same kind of experiment, but with other masses. So in the previous one, we had a 412 versus a 209. Now it's 311, I believe, versus 209. So different masses. And we're just going to see what happens if this formula can also be applied to this different type of mass ratio. So first, as always, he's going to weigh the cards.
Mass 1.
So this is the heavy mass, 311 grams. Oh yeah, also I have done all the calculations beforehand to spare you from all the time, me typing in all the numbers and calculating. It takes a lot of time, so I'm going to spare you from all that. I have already calculated everything, and you just got to follow along. I have you can see my mouse, a big red dot, so you can see where I'm pointing at. So here we see mass 1. Here's all the data in this, over in this square. Mass 1 equals 311 grams, so convert that into kilograms, 0.311 kilograms. Now mass 2.
Mass 2. Okay.
So you got 209.8, which becomes 0.2098 kilograms. Okay, so now the experiment.
I'm going to stick this one on here.
So this is the same setup. We have two photo gates. This one has a red tape, this one has a blue tape. And at the screen, we see also a red tape and a blue tape, so we can get the timings of this one over here. You can see the timings of this one, of the red tape over here, and of the blue tape over here.
One on there. Now watch out, both of these are going to end up going through the blue gate eventually. So you're going to see different times for the blue gate. Watch out for that. Okay, let's get this running. Reset timers. Well, thank you. Timers now reset. Go.
Right, so the incoming velocity or timing is 0.1803. So I put that in here. Time 1 equals 0.1803 seconds. And then for the second card, it is 0.1574, 0.1574 seconds. And then since card 1 is heavier than card 2, card 1 will also keep going in the same direction. It will go through the second photo gate as well, pretty slowly. So here you can see this is the velocity of card 1 going through photo gate 2. The timing 0.88011. So it's T1 prime is 0.8011 seconds. Okay, so now we have the timings, we have all our data. The only thing we need to do now is to convert the timings into velocities. Again, let's assume that the lengths of the cards are 10 centimeters. Again, it doesn't matter what distance you pick. The ratios will always be the same. So let's pick 10 centimeters or 0.1 meters. So that turns into velocity 1.5546 meters per second. And the second card has a velocity of 0.6353, and then the first cards, which keep continuing, which also goes through the second photo gate, has a velocity of 0.1248 meters per second. So now we can, I mean, these are the actual experimental results, and now we will do the predictions. So we use this equation. We use this one, V1F, so the velocity of part 1 after a collision. So we do mass 1 minus mass 2 divided by mass 1 plus mass 2 times the initial velocity. And then we have plus 2 times mass 2 divided by mass 1 plus mass 2 times the initial velocity of the second card. But the initial velocity of the second card was 0, so this whole thing becomes 0. So here are the numbers. And so the result is, the prediction is 0.1077 meters per second. That's the prediction for card 1 after collision, so which is T1 prime. The prediction is 0.1077 meters per second, and the actual result is 0.1248 meters per second. So 0.10, 0.12, the difference of 2, of 0.02. A little bit off, not terribly much. I think it's within the range of acceptable error. Okay, so now the second card after collision. So this is the actual result. And when I do the calculations, the predictions, we get 0.6623 meters per second. So the prediction is 0.6623, and the result is 0.6353, a difference of 0.03. Also pretty close, a little bit off, not too terribly much. Okay, so again, this equation is pretty reliable. The differences between the prediction and the results are not far off, too far off. And then, so these are the velocities. Now let's check for the momentum, the momenta. So we got P1, momentum 1, the initial momentum. So part 1 coming in with a velocity of 0.55 for 46 meters per second times mass 1. That gives us an answer of 0.1724 kilograms times meters per second. That's the initial, that's the total momentum. It's the total initial momentum. So now after collision, part 1 has a momentum of 0.0388, and part 2 after collision has a momentum of 0.1332. Now, since both parts after collision are still moving in the same direction, okay, and let's assume that direction matters, then they both must be added in order to check whether or not momentum is conserved. So we add them together, and we get a result of 0.1720. The initial momentum, the total initial momentum was 0.1724. And when we add the momentums of part 1 and part 2 after collision, we get 0.1720. So really close. Momentum is conserved. It's a really small difference. 1720 versus 1724. Really good. So momentum is definitely conserved. When we apply kinetic energy formula, 1/2 times mass times velocity squared, you can see that for the total kinetic energy, the initial total amount of kinetic energy is 0.04782 joules. For part 1 after collision, it's 0.00242 joules. And for part 2 after collision, it's 0.04203 joules. And when we add those together, we get 0.0445. So this is after collision, the total amount of kinetic energy, 0.004, 0.044, and the initial kinetic energy was 0.047. So a little difference. Again, 0.44, 0.044, 0.047. A little difference. Not too terribly much. So there's always a bigger chance to lose kinetic energy. Okay, so I think all the results are within the range of acceptable error, which proves that this equation is reliable. So now again, I will repeat this in every video. For the opposition, all right, when you have this type of mass ratio, 311 grams versus 209 grams or 210 grams. So 310 versus 210. This type of ratio. What will your prediction be in an ideal elastic collision experiment? Yeah, that's all. The next video is going to be interesting because we're going to be dealing with a small mass colliding against a heavy mass, so there will be a reflection, and so then we will see whether or not momentum is a vector and whether or not direction matters. Okay, see you in the next video.